We have Mike. Okay, good. Welcome back to Monday and our continued discussion of electrostatic forces. Questions at all? Questions about homework? Homework is due Wednesday. We'll have another one that goes out also on Wednesday. Okay. So last time we started talking about Coulomb's law and the Coulomb force and the Coulomb energies that can be calculated, and we derived a Coulomb constant. Okay, and we did a simple problem where we were just given the dimensions, the distance between two forces, and from that calculated charges. Could you do something slightly more complicated if I gave you, say I told you that you had 100 electrons here and 250 electrons here and, I don't know, 432 protons here, and I said, calculate what this would do right here. Yes?
Are we assuming the electrons and the protons and so on are not going to repel each other?
Okay, fine. Let's say that this is 3 coulombs, and this is 2 coulombs, and that this is -5 coulombs. You have some generic charge that's there. So what do you think the first thing you would do? Well, and I'm telling you tell me what this one does. Tell me the forces that are experienced on that charge. What's that?
Do some of the forces equals MA and then you just draw like directions.
Okay, so yeah, it's in the right direction, right? So what are these two going to do? They're going to repel. So what's the net direction going to be on this one?
That way.
Right? So this one's going to go this way. And so this is going to be the force here between, so let's just call this 1, 2, points 1, 2, and 3 generically, right? So then we could just calculate the overall force 1, 2 here. What's going to be the overall direction here? Down, right? This is going to be attractive. And so this is going to be the force 1, 3, right? And so then we could just use some mathematics and Pythagorean theorem then to calculate the overall direction and force magnitude of that charge, right? No big deal? Okay, so there'll probably be a homework to that effect. Okay. So now let's start to think about a lot of what we're going to do today is talking about what's known as the lattice energy. And we're going to basically do two approaches to estimating the lattice energy of an ionic crystal. And we're going to largely use sodium chloride as an example, but you could use this for cadmium selenide in a quantum dot. I'll try to have a homework problem that's more nano related, but the examples today are largely going to be about good old-fashioned sodium chloride because it is a relatively well-characterized ionic crystal. So two ways to do it. One is we're going to further modify Coulomb's law, and the second one we're going to do what's known as the Born-Haber cycle, where we take elements that are more known, different enthalpy values that are more known, and calculate the lattice energy. So ionic bonds, again, intramolecular force or intermolecular force? Intramolecular forces, because it's within this molecule, right? So ion-ion interactions are non-directional. These are, this is not sharing of electrons, right? This is an exchange of electrons. So it's not like there's a polar ionic bond or a non-polar ionic bond. These are non-directional interactions. So the strength of the interactions here, it kind of makes sense, is proportional to the magnitude of the charge and indirectly proportional to the distance between the ions. Okay, so if we have more distance between the ions, less energy holding them together, we have a lot of charge, they're going to stick together a lot more. Okay, and the overall bond energy is the magnitude of these charges and the distances. This term is described the lattice energy because there are many, many ions, and this is generally it's in kilojoules per mole. So it's the lattice energy. It's the energy required to dissociate. Well, let's define it. Lattice energy. Lattice enthalpy is the right way to say it. So delta H lattice. It's the enthalpy required to dissociate 1 mole. The definition is particular, and why these fussy old physical chemists defined it this way, I have yet to get a satisfying answer to. To dissociate 1 mole of solid phase crystal into gaseous ions. Gaseous ions. So do you think that's an easy experiment to do? It's not, right? Like that's a hard, like you could maybe put a pan full of, rock salt on your stove and heat it and very carefully measure how much heat you put into it. But we're going to get off is probably not gaseous ions. And even if you did, the ability to measure how many of these gaseous ions you have and what percentage of them are ions versus gases is going to be kind of hard, right? So this is a difficult measurement to make still, okay? This in units of kilojoules per mole. Okay. Do you remember how many kilojoules per mole do we need to just the thermal energy at room temperature? We had that value. Yeah, like 3.2 kilojoules per mole is what you need to avoid to hold something together, right? And that's just that was equal to 3/2 times the Boltzmann constant T at 200 at room temperature, 298 Kelvin. That was one of the lectures last week. So we have to, hopefully, we have more energy than this in whatever our lattice is to hold it together. Okay? So how could we use Coulomb's law to try to estimate this? If we can't measure it, hopefully we can kind of estimate it, right? Because if we look at a sodium chloride crystal, these are all point charges, right? Or not point charges, but these are each one of these interactions between the sodium chloride is something like this, right? So how could we use that to estimate it? Well, what we can do is start to think a little more carefully about this. And so, did my color scheme change there? That would be really confusing, wouldn't it? It doesn't really matter, does it? No. It does matter in that which one's bigger. Why? Yeah, and it has more electrons. Yeah. Okay. So let's pull that up. So if we were to just pick, let's look at the green one. How many red ones does each green one see? 6, right? So we could start to do, then the energy there is K, Q1, Q2 over R, okay? That was an awful tilde. Times 6. Okay? But is that all that it feels? No. Right? What else does it feel? From the, okay, so are we calling, if this, let's say green and red. So we're now, this was red plus red with green, right? So this is actually negative and plus. Red, green. Okay, so what else is it feeling?
The other greens.
The other greens that are not immediately bound to it, right? So we've got green, green. What else?
The other reds that are further.
Other reds that are farther out, right? Next shell, red, reds. Then the next layer, red, green. Then the next layer, red, red, right? So this can go on and on. Okay, so how to quantitate this a little bit better. Do you know how, so if we were then to go to the next level of red, red, what would that number be?
We're talking about now the corners.
It's hard to see this, so I'm really glad I found this. Whoa! I mean, it's still awful, but it's at least a little bit better. And you've got to, I had to sit here and really study it to convince myself that it's right. So here, 0 is the one that we were looking at, right, at the beginning, right? So this is kind of, okay, so 1, 1, 1, 1, and then above and below, right? So that's the 6, okay? So this is what this is calling it level 1. Okay. So now to go to level 2, we're essentially, so here 2, 2, 2, 2, 2. These are the so if this is chlorine, this is sodium. Now we're looking at the chlorines that are bound to that sodium that was originally bound to the first round, right? And if you go through and calculate, and well, not calculate, but count, there's 12 of these second generation chlorine atoms. Yes?
What does the 2 represent?
2 is just your next, essentially, shell farther out, right? If you're thinking about this almost like spherical, right? So we're looking at the other atoms that are closest, and then the next one's out.
So the 0 acts like a reference point.
It's a reference point. Yeah, yeah, yep. And we're all, and different colors are the different sodiums and chlorides. Yeah. So 0 is like our center. Okay. Again, this is an estimate, right? That we're estimating. But if you count this up, there are 12 in this next round. Times 12. Okay, so how is this going to change then? So E, that's one thing. Yep.
And then your R value is going to be different.
How?
It's going to be larger diagonals, so it's going to have 2.
Exactly. Did everybody? So one thing is that these charges are now going to be the same, right? So if we were calling this chlorine because it's bigger, and in the first round this was negative and this was positive, now this is going to be negative, negative, right? Okay. Now what's R going to be? Here R was easy because it was just the distance between, and we can look that up. We can look that, but here it's going to be a little different because these are from there to there and then over again, where this is a 90-degree angle going into the board, right? So what you can do is it's R and R. So if this is X, right? Because these are equal. So r squared plus r squared, 2r squared, square root of 2r is that distance between 0 and 2. Or between 0 and this 2. Maybe this one's a little more obvious to see, where this is, and this is a 90-degree angle, so this 2 is coming out of the board. Okay? So square root of 2 r. Okay, what about the next one? Red, this was red, red. Now we're back to red, green. So that was level 1. So here we're comparing level 0 to level 1. Here we're comparing level 0 to level 2. Now we're going to do level 0 to level 3. Okay.
Looks like there's 8 of them.
There are 8 of them. There are 8. And the other thing is, when it gets confusing, you would never recount the same one again, right? Because it feels kind of dissatisfying to be like, there's only 8, but if you think about the ones that you've already counted previously, that's how so I had to literally sit there and try this again and like X them off on a piece of paper to convince myself that that was right. Okay, but now we're at 8. And here, our R is going to be different yet again. Because what we're going to get where this is R, this is R, this is R. So now we're looking at x squared equals r squared plus 2r squared. Yeah.
Isn't it r away in each x, y, and z? It's not 2r away.
That's the next level.
Because it's r, and then...
Yeah, there's an X, a Y, and a Z difference.
Because it looks like you're doing 5 right now, not 3.
No, it's 3. You're getting the
So
diagonally across a cube. It's cube. Yeah, diagonally across a cube. Root 3, yeah. Root 3.
yeah. So let's look at so 1, 2, 3 over. Or what's a better one? 1, 2, 3 over. Our next level is going to be square root of 4r, because then we're going to look in both directions. And this can, of course, we could have just as easily done this as, yeah.
Professor, wouldn't the longer arm be a root be the same length that was used for between 0 and 2? So then you're going back root 2 r, and then 2 maybe that's how you get that.
You're saying,
I think that's correct. That's the correct equation, but that's the drawing doesn't.
because this is 2r.
Yeah, that's root 2r, not 2r.
So that should then be,
No. Their equation is correct. Just the drawing should be root 2r as that distance.
Professor, it looks like you're doing opposite corners of a rectangle, and I think we're supposed to be drawing a cube.
You don't have to do three dimensions.
you don't have to do, yeah, exactly.
Two-dimensional square, but then like the bottom length he's saying is root 2r, and then the top length is r, so when you square it, it's 2r squared plus r squared is 3r squared, squared 3r.
Yes. Because you're only, I mean, even though this is a cube, you're looking at a line between this 0 and this one, and this one, and this one, and this one, right? So even though it is a cube, you're only concerned about that line. So then this is now a plus, a minus, okay? And you can tease this out forever, and what we're deriving here is what the book calls the Madelung constant. For sodium chloride. Because then what, of course, you can do is start to call that negative Q1, Q2 over R times 6. We factored out that negative, right? So we're going to keep this as positive. But now this becomes negative. This next round becomes positive. This will go on and on and on. The trick is, well, one of the tricks, then is that you have to consider this both for sodium and for chloride. So if you do this math, you have to multiply it by 2 to get the Madelung constant. The book just states it as 1.748. So what you can do then is rewrite this as, I think they write it as a script M.
Isn't that the energy of the first year?
Thank you. Or, yes, that's how we want it. And so these are all published, so you can look up the Madelung constant for magnesium chloride or whatever you want. Yes?
So they're just different Madelung constants for different crystal.
Absolutely. And it's a function of the packing geometry, largely the packing geometry. Yeah. Okay. So, if the book just drops it like this. So if we were to calculate this for sodium chloride, it would be 1.748 times, these are both monovalent, right? So 1.6 times 10 to the negative 19th. Coulombs squared. Oh, that's that. And then our K, which is 8.99 times 10 to the 9th. What is it? Newtons squared, meters squared coulombs. This is getting a little messy, isn't it? Ah, that's why I wrote it there. Newtons meters squared per coulomb squared. Sorry, that's behind the board. Now, what's R? It's what? Yeah, so if this was ever, this was I think one of the questions on the, hold on just a sec, is that you would have a table like this. Come on.
Yeah.
So what would this be for sodium chloride, looking at this table?
283.
Everybody get that? How it's 283? What do you think the units are here? Yeah. So we're looking for sodium chloride. So this is sodium and that's chloride. So 116 for sodium ion plus 167 for chlorine ion is 283. What?
We don't care if it's like a body-centered or face-centered, because like the R differs for those two shapes.
The R? Yeah, and that would be tricked out in the Madelung constant for that. Yes.
So mathematically, what we're doing to get the Madelung constant is treating those values as a Taylor series and then figuring out the limit.
Yeah, we could have just as easily, if you do it in a line, like positive, negative, right? And you just go from here where it's R, 2R, 3R, 4R, that just becomes the natural logarithm of 2. Yeah.
Should we anticipate being tested on our ability to derive Madelung constants for
No.
different geometries?
Yes.
So the Madelung constant will reflect like whether or not they're cubic or rhombic. Like it'll reflect the shape of it.
Yep. Because and it'll reflect it through these kinds of this kind of the R, how the distance between the ions is going to change, right? Okay. So now if this is over 2.83 times 10 to the negative 10th meters, I think that's right. I get 1.42 times 10 to the negative 19th joules. What do we still have to do to this? Because what did we define our lattice energy to be? Kilojoules per mole. So this is negative 800. Oops, sorry, that should have been negative. 857 kilojoules per mole for sodium chloride. So that's one way of estimating this. Okay. If you read, did anybody read? Yeah.
I put a question.
Yeah.
Lattice energy always favorable for forming the solid?
It better be. Yeah, right? Or else you're not going to form it. Yeah. So did you notice the correction factor that they had in the book? Was that a question? No? So it turns out that this is still not really known. Isn't that kind of, isn't that amazing that like there's only estimates for something like sodium chloride? So when people have done this experimentally, they get something closer to 780-ish. So there's another correction factor that I'm not going to derive. So we keep that same Madelung constant. So this is the summation of repulsive and these are attractive forces from the ions, right? Attractive and repulsive forces from the ions. So positive and negative, if you want to think about it that way, attractive forces from the ions, right? What we haven't considered is the electron-electron repulsion. Okay? And the way that is done is this additional term, which is the electron-electron repulsion. Okay? And this is the complete expression for the lattice energy. Okay, and so D0 then is the equilibrium lattice spacing. Okay, which we already calculated to be 2.83, right? This is a constant, I'm sorry. Change that. D star. And D star then is a constant of 0.345 angstroms. Okay? So if this gets bigger, yes?
So not constant and this repulsion term both vary based on the compound that we're using.
Yes. That's a good question. I don't know. I think this is for I think this is a constant. Yeah. as opposed to a species specific constant. But that's a good question. Yeah. Known known and unknown unknowns. You guys are probably too young to remember that when Donald Rumsfeld said that. Yeah. This though clearly is a function of the species, right? The equilibrium lattice. The equilibrium lattice distance between sodium chloride is going to be different than sodium iodide, obviously. Yeah. Yes.
So what is the equilibrium lattice? Is it like the A lattice constant, or like what exactly is it?
It's again your distance between the two species.
So it's just the A.
Yeah. It's 200 for sodium chloride. It's 283 picometers. Yeah.
So we're just calculating it based on these numbers, as if they were just sitting right next to each other.
Yeah.
The center to center distance.
So here it's our unit.
It's a little bit. I didn't take 116.
Well, yeah, but that's the measurement from the center to the edge. I don't know, the numbers here are the measurement from the center to the edge of the sphere.
I think so. Yeah. Yeah.
So D7 is the same as R,
Yeah, that is kind of confusing, isn't it? Yeah.
Wait, so if you're doing D star over D naught, in this case it would be greater than 1. So you would get 1 minus.
No. This is,
Yeah. So it'd be,
it's less than 1.
but wait, when you divide it by 0.283,
This divided by 280. That's 2.8.
Okay.
Yeah, in angstroms.
okay.
Yeah.
And what's this? Say 0.345 angstroms minus circle No, it's saying it's a constant.
Yeah, this is a constant.
Oh, just
Yeah.
Okay, perfect.
Sorry. So when this then becomes, if this becomes bigger and bigger and bigger and bigger, right, these repulsive forces get smaller and smaller and smaller, which makes sense, right? This stays constant. If you were to pull your sodium and chloride apart, you would have less electron repulsion. And likewise, as we move closer together, you start to have more and more repulsion. Okay? So there'll be a couple problems on this to try to solidify it. Okay? Okay, let's try doing this through a different approach. This Born-Haber cycle. So what this is saying, what this is doing is we can pull things that are known experimentally and use it to estimate the lattice constant through a different way, okay? We can take different, for example, it's kind of it's much easier to measure the ionization energy of sodium, right? We can do electrochemistry and measure how much energy does it take to transfer a mole of electrons from sodium ion to sodium metal. We can do electrochemistry to estimate how much energy does it take to pull an electron or put an electron on chlorine, right? We can literally boil, we can sublimate chlorine gas. We can take chlorine gas and go from chlorine gas to chlorine liquid to chlorine solid. Those are slightly more, those still kind of complicated, but it's still easier than doing what we need to do for the lattice energy, which is go from solid to gaseous ions, right? So what we're doing is taking these different pieces and putting it together. And this is known as Hess's law, that the overall enthalpy change of a process is independent of the path taken. So this is what we're trying to calculate, right? Don't forget these different they're just generic 1, 2, and 3. So if we were trying to go from NaCl, that's what we're trying to do here. Right, everything we've been trying to do today is to calculate NaCl solid to Na plus gas plus Cl minus gas. Okay, this delta H lattice. Okay, so what we just did was an estimate. Now we're going to say, let's measure this. We know this, and I know this, and I know this, and you know that. So let's try to calculate this through a different way. Okay? So we need to define some terms. Boy, that's kind of, we can read that? Good enough? Okay. So the first one is the enthalpy of formation. Okay? The enthalpy change, when, again, we're always going to be molar here. When one mole is formed from constituent elements in their standard states under standard conditions. So all of these are implying standard conditions. I only wrote it there the first time. So standard temperature and pressure. When one mole is formed from constituent elements in their standard state. So standard state sodium is solid. Standard state chlorine is as a gas. Okay? Here's again what we're, oh, that's a typo. Here's what we're looking for. 1 mole of ionic crystal broken into constituent gaseous ions. We can measure the enthalpy of ionization. For example, I wrote magnesium. When 1 electron is removed from each atom in a mole of gaseous atoms. Okay? Enthalpy of atomization. the enthalpy change when 1 mole of gaseous atoms is formed from their elemental state. Okay, so this is boiling sodium. The enthalpy, this is just a typo too, it should be capitalized. The enthalpy of dissociation, when 1 mole of covalent bonds is broken into 2 gaseous atoms or radicals. Okay? And so believe it or not, people spent years of their life measuring these things. And probably they're long forgotten. But their numbers live on, right? Isn't that amazing? Their numbers live on without them, even though we have no idea. Well, it depends. Do you want them to remember your name or your numbers? Or do you want them? I don't even really want to be remembered. They can all forget me. Okay. We're going to try to rock this out. Okay, so what we're going to do is just illustrate this graphically. And so you went into the literature and you pulled this stuff up. Has anybody seen a CRC handbook? You know what a CRC handbook is? They're like this big and they're just full of tables of this kind of crap. So you can find all of these numbers, okay? So what we want to do, what we want to do is we're essentially going to just add these up. It's really quite simple. We're going to add these up, but it's just how do you do it in the right number, how do you do it in the right way, and how do you have the terms be correct, okay? So this is a graphical way of doing it. Let's do the lights again, Rosie. So what we want to start with is what we're starting with is sodium chloride solid. Okay. So of all the things that we have here, the only thing we can do is our enthalpy of formation. And let's draw a down arrow indicating that that number is negative. Okay? So this is our delta H of formation. And our delta H of formation was by definition coming from Na solid plus 1/2 Cl gas. Okay? What we're trying to do is get to these. Right? We're just going to walk step by step. We're going to do some ionization. We're going to do some atomization until we get to this step. Okay? Ionized gaseous species. Okay? So what can we do with solid sodium? Let's do solid sodium first. Right? We can atomize it. Right? We could just as soon mess with chlorine first. We could say, let's mess with chlorine first, and then what would we do? We would probably dissociate it, right? But let's do sodium first.
Could you write a 2 next to chlorine? 1/2 Cl2.
Thank you. 1/2 Cl2. That is the worst 2 I have ever seen. Okay. So we're going to atomize sodium. Atomization of sodium is a positive number. So we're going to write this as an up arrow, delta H, atomization for sodium. Okay? We can write the numbers down too. So plus 107, this was minus 411. Right? These are all kilojoules per mole. Okay, so now we've atomized sodium. I still am bringing this along for the ride, 1/2 Cl2 gas. Now what do you think I want to do? Remember, I want to ionize it. So ionization of sodium, positive 496. Delta H, ionization, sodium. So now I have Na gas plus 1/2 Cl2 gas. Okay, so I'm done with sodium. Now I've got to mess with chlorine. So same thing with chlorine. We can dissociate it. Or I'm sorry. Yeah, we've got to do both, right? So we can, am I getting lost here? We can, we have to atomize it first.
Is that a typo or is it called ionization for that as well?
Where are you looking?
There it says delta H atomized of chlorine. Oh, which one's the
Middle one.
That one? So right here it says delta H atomizing chlorine, but then down here delta H dissociating is how we. So I'm guessing this is
Thank you.
dissociation right here.
Yes. That's. Hold on. You have to. We're going to atomize it. Yes, is what we're atomizing. Well, yeah. This is. You're right. This is dissociation because it's already in gaseous state. Yes. So that should be dissociation. Okay, so now we've got Na gas plus Cl gas, and that was a difference of 122. And now we just have to ionize our gas, which is a down. So Na gas plus Cl gas minus, and that was our blah, 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 349. Yes?
We have to take the 1/2 factor because we're only dealing with half of the...
We've been writing it by, that's a good question. The way this is defined, the short answer is no, because the way that this is defined, if I will be consistent if this was written as 1/2 Cl2 to 1 Cl, that number would have been twice as big. But so people do it different ways is the long answer. The short answer is you don't have to worry about it here. Unless it was a divalent system, right? In which case you were transferring 2 electrons. You would have different ionization energies, and you would have to consider it twice. Yeah. Okay. So then this is our X. This is our delta H lattice. Okay? And you can kind of just think of going backwards along this path and just add these up. Okay? I like thinking about it this way. So we're going to do, if we're going backwards against this path, this is going to become positive. Let's just add then a negative 122, a negative 496, a negative 107, and then we're going with this one, so it's negative 411. Because we're going in the same direction.
But then why was 349 positive?
Yeah, you're right. Because the reaction pathway is going against this direction, right? In the overall formation of this, you're going first from gaseous ion against 2 gaseous chlorine atom. This is the direction that you're going.
But if the delta H lattice is the
sum of all the other steps. How come we have a down arrow that we're adding and a down arrow that we're subtracting?
Because of the way that these are, the convention that these are written. We're out of time. We'll touch base on this again next class.